Hi, my name is Mark Falco, and in this presentation we'll be discussing configuration changes to Oracle Coherence 12.2.1. The set of changes we'll be talking about focus around zero configuration for coherence. So what is zero configuration? Well, you're all familiar with it. When you use DHCP rather than static IP, what happens? You plug your laptop into a network and somehow it manages to get an IP address assigned to it that doesn't conflict with other IPs on the network, and you didn't have to work this out ahead of time with the sysadmin and plug the IP in yourself. It just happens automatically, right? So this is a primary example of zero configuration, but in essence it means how do you have a system configure itself? And in reality, it means less configuration on the end user. So in 12.2.1, we looked at how to do this with coherence, and we focused on a number of pain points: network port selection, the WKA list, the out-of-the-box cache configuration, and sizing of thread pools. Each one of these things consists of a small number of configuration changes to coherence. On their own, they're nice, but not any big deal. When you put them all together, though, you get an experience which hopefully will make it much easier to get coherence up and running than it was with previous releases. So let's start by talking about networking. And in fact, let's talk about networking and coherence in older releases, pre-12.2.1. So first we had cluster discovery, and that was done in one of two ways. You either had the cluster discovery running over a particular cluster address and port, or you used the well-known address feature of coherence, which was you configure the cluster with a series of IP address port pairs where coherence can look for cluster members in order to join the cluster without needing any multicast. Also, in older releases, each coherence cluster member, each process, would use two UDP ports to talk to other cluster members. And those ports were selected from a range starting by default at 8080 and moving all the way up to 65535. The way that worked, we tried to bind to port 8080, and if we failed to bind to it, we tried to bind to port 8081. Once we successfully bound to one port, we continued this process to bind to our second port. Why did we use two ports? Well, it was one for send, one for receive, and we found that on certain OSs we actually got performance gains from that with UDP sockets. So this simple port selection strategy was sufficient for avoiding port conflicts with other coherence cluster members of the same cluster. So you could start a whole bunch of nodes on the same machine, and they would they'd all try to get 8080, and only one would get it, and the next one would grab 8081, and they may interleave, but you'd end up with a series of ports selected for coherence, and it would never iterate all the way up to 65535, but it could. And this worked quite well for coherence. Where it didn't work well was for anything else that may have been in that range of ports. Coherence, just incrementing the port until it found an available one, could mean that ultimately we could start stepping on ports which the user didn't intend us to. So for instance, if for some reason the number of those ports in the 8,000 range were taken, it's possible that we start stepping up into the 9,000 range, and that could conflict with other processes running on the box. So again, coherence did pretty well on its own, but when other software was involved, we could end up stealing a port from them. Also, or similarly, if you were running two distinct clusters on the same machine, and you were using a WKA configuration, you could, through the same sort of problem that I described with other software, you could end up incrementing the 8080 port until it stepped into the range that was used as a WKA address for another cluster. Now the two clusters can see each other, and well, that coherence didn't like that and would start issuing complaints. Finally, we talk about the coherence extend proxy. It used just one TCP port, and the configuration for that port was fixed. So say you configured the proxy to run on port 9000. If you wanted to start two proxies on the same box, they would need distinct configurations to avoid having a port conflict when the second one started. So moving on to 12.2.1 discovery, we've tried to address these issues I just described. So first, we introduce a singular cluster port concept, and this applies to both multicast and WKA, where previously I described with multicast discovery, you had a multicast address and multicast port. With WKA discovery, you had a series of unicast port pairs. So you might have had 192.168.1.1 port, 8080, and then 192.168.1.1 port 8090, and so on. Instead, with the singular port concept, we say there's a cluster port, and all members in the cluster are configured with the same cluster port. And regardless of how many members you run on a machine, all of them effectively share that cluster port, and all machines in the cluster use the same cluster port. So it's a simpler configuration concept, rather, especially when you look at WK, where you had a series of, port numbers over, any particular range. This makes WK configuration far more like multicast. We have a single port to think about and to allocate for coherence. 12.2.1 remains UDP based by default. The WKA list, though, now that we have the cluster port concept, ports are removed from the WKA list. So it is just a list of IP addresses. And to further simplify that, since it's only IP addresses, you could actually store that list of IP addresses in your DNS server under a single address record, perhaps using a cluster name. So if I had a cluster named Mark's Cluster, I might create a DNS record called Mark's Cluster and store my entire WKA list in DNS. Then in my WKA configuration, I can just put in that sort of virtual host name, Mark's Cluster. Coherence will, at runtime, query DNS, get the entire address set back out, and use that for starting the cluster. What this does is it centralizes the management of that list into the DNS server rather than into your configuration file, which is being manually replicated onto all the machines that are going to be in the cluster. The cluster port and the multicast port are the same thing. So if you're not using WKA, when you configure the cluster port, you're configuring the multicast port. In fact, I really said that backwards. The place that the cluster port is configured is the multicast port configuration. This has always been referred to as the cluster port. It just now also applies to WKA configurations as well. One other very nice feature about this is that port is actually shareable between clusters. So if you're going to run two clusters on the same multicast address, they can share the same cluster port. And in fact, if you're going to run two clusters on the same machine, and they can be multicast or they can be WKA or a mix of either one, they can also share a single cluster port. So what this means is that you really don't have to think about selecting the cluster port for your cluster. In fact, you can safely use the out-of-the-box default cluster port, which is 7574, and that has been registered with the IANA, basically the Internet Authority on port numbers. That's been registered to Coherence. So you can just leave the default as it is and not have to worry about conflicts with other Coherence clusters running on your network or on your machine. And ideally, you shouldn't have to worry about port conflicts either, as that port is technically registered only for use with Coherence. So anything else using it, they weren't registered, so they're the offender. But obviously, you can always change Coherence to run on a different cluster port if you wish. So if there's multiple clusters running on the same port, how do we differentiate them? Well, Coherence has long had a cluster name concept, and this now becomes the unique identifier for a cluster. Because the importance of the cluster name is increased significantly, we've also increased the maximum legal length of a cluster name up to 64 characters rather than the previous limit, which was only 32. So it's suggested that when assigning a cluster name, especially for production use cases, that it have a name that's highly likely to be unique. So Coherence cluster would be a bad choice of cluster name. Also, the example I use in this presentation of Mark's cluster, bad cluster name. But something where it's your product Coherence cluster or your product cluster, this might be more reasonable. What happens if you have a collision and two clusters chose the same name? Well, those aren't two clusters then. Those are supposed to be the same cluster, and we will try to have them, any nodes that have the same cluster name, we'll try to have them form a single cluster, and if we can't, we would consider that an error. So choose your name wisely. Also in the discovery arena, we've changed how extend clients discover the proxy. So prior to 12.2.1, proxies listened on a single configured IP. It happened to default to the loopback adapter. Now the proxies listen on the wildcard address. So they effectively listen on all IPs on the machine by default. And a client can discover the proxy in a different way than it did in older releases. Effectively, what an extend client will now do is they can be configured to discover the cluster, and once they've discovered the cluster, they can find their proxy. Whereas in older releases, you had to have the explicit IP import of the proxy you wanted to connect to. Now it's more of a true discovery process, and that discovery actually can occur using the standard cluster configuration. So if an extend client has a cluster's operational config, this is the Tangocell Coherence override XML, the extend client will look into that and see how the cluster was configured, if it was configured with multicast or WKA, and it will turn around and use the same basic technique that cluster members use to discover the cluster. The extend client, which is not a cluster member, will use that same technique to find the cluster and then ask it where the proxy or proxies are running. And so clients can effectively discover the cluster over multicast or WKA. And it should be pointed out that even a cluster which is running on multicast could still be discovered using effectively a WKA-like procedure. Basically, you can configure the extend client with a set of IP addresses of any members in the cluster, and it'll use that to find the cluster and then find the proxy. Obviously, multicast is easier, but if you're in a situation where the extend clients are on a network that doesn't support multicast and the cluster is using multicast, you can still discover the cluster through unicast addresses without having to point specifically at a proxy. You point at any cluster member and it'll redirect you to the proxy. And again, like I mentioned for WKA, these lists can be, the list of unicast addresses, or the WKA list, can be stored in DNS. So an extend client, given a kind of virtual host name that represents the cluster, will turn around and extract that full set of IPs from the DNS server and use that to find the cluster. So looking at this in a little bit more depth, looking at WKA Discovery in more depth, we see that now a WKA list is just simply a set of IP addresses. And a common misconception regarding WKA is that it has to be an exhaustive list of all cluster members, or now that we don't have ports of all machines. It doesn't need to be. If you had 100 machines in your cluster and you had a WKA list consisting of just one machine, and there was any cluster members running on that machine, we would be able to discover the cluster. Obviously, having an address list of just one machine isn't particularly good for HA, so you want to have a decently long list without going through the trouble of trying to make it exhaustive. A longer list is only going to help in terms of HA. So typically 3 or 4 addresses would be sufficient, right? You would be able to lose a couple of machines and still find the cluster. I generally recommend no more than 1 or 2 addresses per kind of unit of failure within the cluster. So, for instance, per switch, you might have 2 or 3 WK addresses. But I really discourage people from trying to put in the exhaustive list, mostly because, well, it's exhausting. You don't need to put that much information in. And again, the second example here shows how if you turn around and store this in DNS, what's actually stored in the cluster configuration then is simply a fake host name, the name of that DNS record. So in this example, Mark's cluster, and then in the DNS server, we would associate all of these addresses with that host name. Also related to WK and zero configuration, when you run on a machine that's multi-homed, a machine that has multiple IP addresses, Coherence has to select which IP it's going to use. Now you can explicitly tell us which IP to use, or you can tell us the subnet that the cluster is running on, and we'll choose a local address in that subnet. But if you're using WKA and you haven't told us a specific address, we'll look at the addresses in the WKA list and infer a subnet from that, and then choose the local IP that best matches that subnet. So in the example here, if I was running on machine 192.168.1.1, while that's not in the WKA list, we would look at the list and say, given this list, it would be best if we chose our local IP that's also in that same subnet. So at least with WKA configuration on a multi-homed machine, you really don't need to worry about setting the specific IP that any given member will use to communicate with the cluster. We infer it just fine. If you're using multicast, well, unfortunately, we really can't infer it then, and we continue to make a best effort to choose the most appropriate IP address, which we choose one that's network routable. So we're not going to choose the loopback adapter, for instance. And assuming there are multiple network routable addresses, we're going to look for the one that appears to be fastest, which the way we determine that today is the one with the largest MTU. But basically, if you're using multicast on a multi-homed environment and our auto selection algorithm doesn't land you where you want to be, then you're going to want to set the unicast address manually, and then I would suggest you actually set it to the subnet again, so that you can at least use the same identical configuration file for all cluster members. And that feature, setting it to a subnet, that's been around for quite a few Coherence releases now. Looking a little closer at Proxy Discovery, here's an example XML element for, this is part of the cache config actually, for how you would configure a remote cache scheme. So in prior releases, you would actually have had a initiator config element and specified one or more proxy IP ports, kind of hard-coded where your proxies are going to reside. And that's still supported in 12.2.1, but the simpler and preferred approach is, as I mentioned before, rely on cluster discovery, and then once the cluster has been discovered, allow the extend client to look up the desired proxy. And the way that works is we look up the name of the proxy. So there's the proxy service name element that refers to the name of the proxy service that you wish to connect to. So once the designated cluster has been found, then we'll look up the proxy. Now, note I did say designated cluster. So now cluster name is actually a concept known to extend clients as well. While the clients aren't part of a cluster, they do have the concept of the cluster they wish to connect to. So if I want my client to connect to Mark's cluster, I'm going to need to tell it that. So that can either be stored in the operational config for the extend client, and then anytime we go to look up a proxy, we'll be looking up one in that cluster. Or you can override it within the remote cache scheme itself. Along with the proxy service name element, you can also specify a cluster name element. That would be typically used if you had an extend client that was going to connect to multiple clusters. So you may have your primary cluster and you store that name in your operational config, and then if there's a secondary cluster you're going to connect to that has a different name, you could put that in a particular remote cache scheme, in which case Discovery would look to find that cluster by name, and then continue to look up the proxy service within it. The feature of having an extend client discover a cluster using its operational config is currently only a feature of the Java extend client. The C++ and .NET clients, right now, they don't introspect their operational config for those configuration elements. So they still need to be configured with a bit more information, although still they're able to avoid the pointing at a specific proxy they wish to connect to. They make use of the within the TCP initiator, they make use of the name service addresses. So basically, this acts like a WKA list. So you tell the extend client, here's a set of IPs at which you may find a cluster member, and once you've found that cluster member, then look up the named proxy service that appeared higher in the configuration. And again, this can use the DNS address expansion feature that I mentioned earlier. So it could be as simple as what we see here. I've stored my WKA list, or the equivalent of it if I'm using multicast, right? I've stored a set of IPs for machines that run my cluster. I've stored that in DNS under the name that's the name of my cluster, and if I'm and then the cluster port for that cluster, which here we're using the default of 7574. So moving on, so we've talked about discovery. Let's talk about port conflicts. As I mentioned on an earlier slide, prior to 12.2.1, Coherence by default started by trying to bind to port 8080, and if that was unavailable, it moved forward a port, and we continued this process until we find a free port. And as I mentioned, that worked well for Coherence avoiding conflicts with other members in the same cluster, but it did not work all that well if there was other software running on neighboring ports. We could end up stomping and on those ports, taking them over and holding them when the other software wanted to have it. So how do we do a better job in 12.2.1 and avoid the need for manually managing the ports by the end user? Well, first off, as I mentioned, we have a cluster port concept, and what we do is one cluster member per machine will listen on that cluster port. That which member does that is something that Coherence manages itself, but there are some obvious things. The first Coherence process to start up on that machine is going to have to listen to that port. So basically, it's whoever got there first. And when that process dies, there's an automatic handoff to one of the other processes, Coherence processes running on that machine. And there's an interesting question here of, well, what if I'm running two clusters on that machine? Well, the clusters, basically we don't worry about which cluster gets the cluster port. Cluster members running on the same machine for distinct clusters have a minimal awareness of the fact that there are other clusters running on that machine, and they'll forward any discovery packets that arrive on the cluster port. They'll forward it to the correct cluster running on that machine. And again, this is not something that anyone needs to configure. It just happens automatically, and the protocol is written in such a way that it's meant to be future-proof. So it will allow you to run, say, when 12.2.2 comes out, you will be able to run a 12.2.2 and a 12.2.1 cluster on the same machine using the same cluster port. They just need to have different cluster names. So that handles the singular cluster port concept. But what about the individual ports used by each cluster member? Rather than using this 8080 or 8088 and incrementing up, we use OS assigned ports. These are ephemeral ports, which the operating system knows has a range of ports that are meant to be assigned by it to any sockets which are opened on an unspecified port. So Coherence now makes use of that standard facility, which means that we won't try to take a port which is currently in use by other software, but we're taking a port which the OS will never assign to another piece of software. So this is, for instance, when you open up a TCP socket to connect to something remotely, it has a port associated with it, and that's also an ephemeral port. So this is a very standard way for software to have ports assigned to it. But they're effectively random, and they will be high numbers, right? They'll be 50,000 or 33,284, and they'll change from invocation to invocation. So these are not things that you would ever try to write down in a config file. But Coherence, the discovery mechanism, which runs through the well-known port, the cluster port, once we've discovered the cluster, we're able to learn the ephemeral ports assigned to each cluster member, and then we're able to communicate with them. So again, this just ends up meaning that it's easier on the end user. These random ports really aren't important to the end user. It's only important to the cluster members that are up and running at that time, and we're able to share that information through Coherence. A little bit more on the networking side is we've also changed a rather important default of what's the reliable transport used within TCMP. So TCMP is the underlying clustering protocol within Coherence, and historically it's run over UDP in our own reliable UDP engine. A number of versions ago, I think starting with 3.7.1, we introduced a new API for reliable transports called the message bus. This actually came out of the Exalogic Exabus project. We had produced a TCP implementation of Exabus called the TCP message bus, or TMB for short. What we found over the last couple of years is we hardened the TMB implementation and performance tested it. It's actually equaled and in many cases surpassed the performance of our legacy UDP reliable transport. So starting with 12.2.1, we now default to TMB. Now that doesn't mean that we no longer use UDP. UDP is still our default for cluster discovery, with UDP multicast or WKA running with UDP unicast. But once the discovery process has been completed, starting with 12.2.1, we switch over and use TCP for all basically data traffic. The next thing we talk about with ports is the proxy. And I had mentioned earlier that prior to 12.2.1, the proxy was configured with a specific port. Starting with 12.2.1, the proxy actually just shares a TCP port with the rest of the process. So TMB and TCP ring, which is another facility of Coherence that uses TCP, all three of these technologies actually share a single port. And what port is that? Well, it's the ephemeral port that was assigned by the OS. We do attempt to get the same UDP and TCP port, so we do an ephemeral port selection on one and then try to explicitly bind to the other. But if we can't, we'll then just select an ephemeral port or unique ephemeral ports for both. But the net effect should be that when you look at a coherence process, you should see that it's only listening on one given port number, and it's listening on that for both UDP and TCP, and it's a random or ephemeral port number. Now, there is an issue with using these random ephemeral ports in that since you don't know what the value is until runtime, it makes it rather hard to configure a firewall to let them through. Generally, we don't recommend that a coherence cluster members be firewalled from one another. They should be operating in a coherence cluster generally operates within a single LAN, many times within just a few switches, and network performance is key. So generally, we don't see people running firewalls between their cluster members, but it does come up. If you are running a firewall between cluster members, then you're not going to want to use the ephemeral port feature, and instead you're going to want to manually assign ports. But again, we want things to be easier there, and certainly a goal is to allow the same configuration file to apply to all cluster members, and not to have to do port assignment on a member-by-member basis. So what we have now, if you are going to do manual port assignment, you can assign Coherence a range of ports to use, whereas the old range, or in older versions, you had this range of 8088 up to 65535. Now you can specify both a lower and upper bound and know that Coherence will only select ports within that range. So if you were going to run, a dozen members on the same machine, you could set that range to be a dozen ports, or you might want to leave yourself some headroom, say 24 ports. Just open up that range in your firewall, and you'll know that Coherence will operate within that range. And this way, because it's this range, you can have two members on the same machine started concurrently, and they'll just sort out any port conflicts between each other and still be able to come up sharing that same config. And Presumably, you've chosen a range which doesn't interfere with other software running on the box, so you won't have to worry about them somehow, stepping up into a high enough range that they're conflicting with other software. But as I said, we generally, for performance reasons, don't recommend firewalls between cluster members. And if you're not using firewalls, the ephemeral port feature that's what's configured out of the box should be sufficient and the easiest solution for port assignment. So I'm going to go just briefly into a little more detail on the TCP message bus. It doesn't have a whole lot to do with zero configuration, but it is a rather fundamental change in 12.2.1. So as I mentioned, all non-discovery traffic, or we can really say all data traffic, now effectively is transported over TCP rather than UDP. And we have seen workloads where this really does provide a performance benefit. Discovery does remain UDP based. Primarily that would be because of multicast, which is a UDP specific technology. It is possible to do WKA Discovery over TCP, but that means that there are a lot more TCP connections open than would otherwise need be. But for now, Discovery is UDP based, and once we know where things are, then we create TCP connections and run them through the TCP message bus. This does not mean that we have replaced TCMP, the coherence clustering protocol. TCMP makes use of the message bus. It's not that the message bus replaces it. So there's a layer of TCMP, which is the reliable datagram layer, the reliable UDP layer, and TCMP knows when that it's been configured with a message bus that it will bypass that layer. But there's much more to TCMP than just the reliable UDP engine. TMB has been optimized both for high throughput and for low latency. Some of this or a lot of this actually came out of the UDP datagram engine. It's basically noticing when the packet volume is low, we try to just push packets out on the network as quickly as possible. So, for instance, whatever thread tries to send a message, when using TMB, that thread will actually try to put the corresponding packets on the wire. But if the send rate is high enough, then eventually the network will start to push back, and rather than holding the sending thread, whichever thread tried to send the message, will offload that to background threads to allow them to continue the push. So this is when the rate traffic volume is low, we optimize for low latency. As the traffic volume ramps up, we're willing to pay the cost of handing the message off and the packets off to a background thread, which will work to push them out as quick as possible and give us higher throughput. Also, another one of the low latency advantages is when messages arrive at a server, or actually a client for that matter, the thread that it arrives on is a dedicated I/O processing thread. Will identify if it's a simple task. So we've received a request or a response, and if that request has been identified as sufficiently simple, we'll process that request in line on the I/O thread rather than handing it off to the dedicated cache service threads for processing. So this is, again, an optimization to reduce latency. And namely, it reduces latency by removing context switches from the flow of the request processing. Another design aspect of TMB that's important, especially in comparison to the legacy reliable datagram, UDP datagram engine, is that TMB was designed to be able to leverage the massively multi-core machines that are now very common. So as we create TCP connections between all members in the cluster, each member has a non-blocking thread pool for processing those connections, where the legacy datagram engine had a few single-purpose threads. So for instance, there was one thread that was responsible for doing all receives and another thread that was responsible for doing all sends. And there's a couple other threads, but basically it could scale up to, that engine could scale up to 4 threads. And once that had happened, we weren't going to get any more CPU dedicated to running the coherence network tier. TMB will scale itself up to a much larger number of threads and cores based on a number of kind of ergonomic features. So it looks at how many cores are in the machine, how big a JVM was started, how large the cluster is, and it tries to select the proper size for that non-blocking thread pool. This is part of what helps it to get higher throughput as well, is we don't have to worry about maxing out a single core on processing. Say, maybe we could get 12 connections processed by a single core, and then we've maxed out that core. Well, with TMB, we can move on and use multiple cores to process other connections. Another key advantage of TMB, or actually the message bus architecture, is that it offers multi-point flow control, which was something that was never implemented in our legacy UDP reliable transport. And what that multi-point flow control is if we have a message that we're sending to multiple points, right? Say a particular or common example is an event. So a data update is made within Coherence, and we need to send that corresponding event out to many clients in the cluster. So we have a single message going to many clients. Our UDP engine doesn't know how to employ flow control for that, and it just sends it on the network immediately, even if the network is currently in a backlog state. With TMB, or with any of our message buses, this would apply to the Exalogic InfiniBus as well. We're able to take a multi-point message and send it aggressively to the members that we can, and slower for the members that we can't. So it should reduce, basically it means we're not going to continue to throw packets at a network which doesn't want them because it's backlogged. We'll actually throttle ourselves more efficiently than we would have previously. And this is actually a key feature in being able to move away from using multicast for data transmissions. With multicast clusters, multi-point transmissions were quite efficient because multicast meant that a single send could satisfy multiple members. With TCP-based clustering, we actually have to do distinct sends to each of the target members, and it becomes important that information, those transmissions are flow controlled. TMB offers us that. All right, moving out of the networking tier, we also did work in the cache configuration tier. So prior to 12.2.1, what was our default cache config? Well, it was an example. It was documented as an example. There was a big comment at the top that said it was an example. It was not meant to be used in production. Some of the things that you can look into it and see that why it wasn't meant for production. There was an 8 megabyte limit per cache per server. So that was the default high units. You store more than that, and we start evicting other entries to save space. It also had a 1 hour expiry. So we stuff something in the cache, and an hour later, it's magically gone. And there was also no thread pools configured. So you could be sitting on a 32 core box and have 100 clients throwing requests at you, and they were being processed on a single core. This was just what was in the legacy example cache configuration. The scary thing is some people use that in production, and I've always been surprised when I look at a customer's cache configuration and I see that it is either literally our example, or they took our example and made some small modifications to it to suit it to their needs, which is there's nothing inherently wrong with it. Hopefully they removed the 8 megabyte limit and the 1 hour expiry. Sometimes they hadn't, which is why we were looking at their support issue. But really, it wasn't meant as something for production. It was really meant to highlight a variety of features within Coherence. And the way it had done that is through cache name mappings. So we had all these mappings at the top of the file that said if you try to access a cache with a name that starts with dist, then you obviously want a distributed cache. REPL, you want replicated, near, op, local, flash, RAM. These honestly are not good names for caches. If you think of a cache name to be similar to a table name in a database, um, you know, it's you wouldn't start your tables with the name relational. It's named after what it is. Employees, for instance. Another issue with the legacy out-of-the-box cache config is it actually wasn't usable by extend clients. There was no remote cache scheme in it, so extend clients literally had nothing. They couldn't do anything with the file, but it also wasn't particularly compatible if it was used server-side and then an extend client connected to a proxy that was using it. The extend client would pass through their cache name, say employees, and the proxy would resolve it against its cache config and see where employees map to. And it wouldn't obviously map to any of the patterns here, so it would just follow the default mapping, which thankfully was a distributed cache or a partition cache. But still, you had to go and author a custom cache configuration for your extend clients, and it would look very different from the example we ship with. And also, it was rather difficult to author a cache config that applied to both extend clients and to cluster members. So we try to improve this for 12.2.1. So the default cache config in 12.2.1 is not an example. It is something that is considered to be usable in production, but it also is not the answer to everyone's needs. It's expected that people will edit it or replace it. Obviously, if you already have a custom cache config, there's no reason for you to drop it and use the default. But if you're new to Coherence, it's likely that you can get quite far with the default. And when it's time to start customizing your cache config, it would be reasonable to use this the new default as a starting point. Take that cache config file and start modifying it to suit your needs. So how is the new cache config different from the old? Well, to start with, in the new cache config, all caches are partitioned caches. This is what Coherence is about, partitioning. We don't highlight the legacy cache configurations, such as the replicated or optimistic cache. They're still there. You can still configure them, but realistically, nearly all Coherence deployments are on the partition cache technology, and that's what we focus on here. So gone are the dist-star, repl-star. We simply have a single star mapping that say all caches are of one type by default, and that type is partitioned. There's no size limitation on those caches. You may want to put one in, but we're not going to throw data away by default. Obviously, you don't want to store more data than your cluster can handle, but it also, you don't want us to just start throwing away at the magic 8 megabyte boundary either. Caches are also configured to be measured in bytes by default rather than in the legacy cache config. They were measured in terms of entries. Where does this come into play? Well, if you look at the cluster using JMX, the cache units will now be reporting byte sizes rather than entry counts. You can still see the number of entries that's reported with a different element, but the default unit calculator is the binary unit calculator now. Also related to that is the unit factor. For historical reasons, it was not possible to configure size limitations that were larger than 2 gigabytes. This comes around from Java's sizes being expressed in assigned int, so 2 gigabytes being the maximum size. Quite a few releases ago, we introduced unit factor, so you can say, I want my cache units to be counted in kilobytes or megabytes or gigabytes instead of bytes if I'm storing more than 2 gigabytes in an individual cache server. To make things easier, we've now set the unit factor for you. So if you set your high units to a value larger than 2 gigabytes, we'll automatically set the unit factor to an appropriate size so that high units is meaningful. So for instance, if you set your unit factor to 16 gigabytes, we're going to set if you set your high units to 16 gigabytes, will automatically set the unit factor to 1K, and your cache units will be measured in kilobytes rather than bytes. What does any of this means? It means you don't have to set the unit factor. Another significant change in the default cache config is that we employ near caching by default. So all caches are near caches. They're near caches backed by partitioned caches, but a client, when it accesses the cluster, will near cache any data that it retrieves from the cluster. That gives quite a significant performance boost when you're doing repeated reads, right? The first read you pay network round trip time to obtain the data, and the second read is virtually instantaneous. We don't have to go out of process. We already hold that data. Why didn't we do this in previous releases? Well, there are expenses to near caching, but they have been significantly reduced in 12.2.1, specifically the cost of registering for the events for near cache. When you do that initial read, as I mentioned, you have to tell the cache server, I would like to hear any changes that occur to this thing in the future because I'm holding a cached copy of it. And in prior releases, there was a network round trip in order to express interest in a particular key, and then a second network round trip to obtain that the associated entry. In 12.2.1, that's been collapsed down to a single trip. So the overhead of a near cache is, at least the latency overhead, is significantly reduced compared to what you would have had in prior releases, making it a reasonable candidate for being on by default, and you can get quite a significant performance boost if you have the repeated reads. It is possible to disable the near cache, and this is done with the coherence.profile system property, which can be set to either near for near caching or thin. So this, when it's set to thin, it's you're reducing the footprint of the client. You're making it a thin client, and it will always have to go to the cache server to get its data. That system property is only known to the cache config itself. If you take a look at the default cache config, you'll see that property there. If you're using a custom cache config, that property has no meaning. Another rather significant change that comes from the new cache config is that cache servers or servers are storage enabled by default and clients are not. Historically, all cluster members in Coherence were storage enabled by default, and it was put on the customer to have their clients opt out of being storage enabled. That was a good choice in Coherence 1.0, where typically you didn't have cache servers, you only had storage enabled clients, right? But over time, the popular trend with Coherence has been to have a dedicated storage tier and a dedicated client tier, and having to opt out every client was problematic. And when people forgot to opt out a client, that client would become a server and kind of have a more important role in the cluster than was intended. So with 12.2.1, the way that the default cache config has been constructed is that only servers, or more specifically things that respect the auto start element of the cache config, are storage enabled, and things that don't respect the auto start are storage disabled. So what does that mean? The default cache server, when you start Coherence, it'll start up as storage enabled services, but if you just have a plain old client using that same cache config, it won't be storage enabled. The standard Tengasol Coherence distributed local storage system property is still respected. And again, this is just something that is known to the cache config, but it is still respected. So if you want to storage enable a client, you can use the system property to do so. If you want to storage disable a server, you can use the system property to do so. And if you're using a custom cache config, not based on the 12.2.1 cache config, the rules haven't changed from prior releases. So your clients will still be storage enabled then. It's just a cache configuration concept, but one that you may wish to copy into your own cache config if you are doing a custom config. Similarly, all servers are also proxy enabled. So historically, you had to use a system property to indicate that a particular cluster member was going to run the proxy. And some of this came about because you also had to say what specific local address and local port that member was going to run on. For 12.2.1, we're trying to make the proxy tier, the storage tier 1. So by default, every cache server is also a proxy. When connections come in, they get load balanced across all servers, and you have higher HA. It should be a good thing, and it just makes things simpler too. You don't have to think about where you run your proxies. You just start a Coherence server, and it is hosting Coherence services, including storage and proxy connections. If you're not using Extend, you could choose to disable the proxy, but honestly, it's so lightweight. There's a couple of idle threads and a little bit of memory used. It really shouldn't be impose any performance penalty for having an unused proxy running in the cache server. But again, this is just a feature of the default cache config. Now, this cache config, as I mentioned earlier, one of the problems we had with the old one was that you couldn't typically use the same or easily use the same cache config for both cluster members and for Extend clients. This new default cache config has been written in such a way that it is compatible with both. And in fact, it's compatible with Extend clients, cluster clients, and cluster servers. And there's a single system property known only to the cache config that identifies what type of client it is. It's either a direct client, which means it's a cluster, a TCMP-based client. It has a direct connection to the cluster, or it's a remote client, meaning it's an Extend client. So you take the out-of-the-box config, you set this one system property, and all of a sudden your process is running as an Extend client rather than a TCMP client. Another big change, which I won't go into a tremendous amount of detail on, is the thread pools. So again, historically, we didn't have a thread pool enabled by default, and now it is enabled by default. And it's not just that it's enabled by default, it's a new thread pool implementation. It's an auto-sizing thread pool where we constantly monitor the load of the requests coming into the servers, and we increment or increase and decrease the size of the thread pool in order to maximize throughput. So again, the idea is rather than trying to find just the right thread count for your particular service, you can let Coherence figure this out on its own. And this can be pretty dramatic depending on the service. The proxy service definitely benefits a lot from the auto-sizing thread pool. And we had prior versions of Coherence have actually defaulted to an auto-sizing thread pool in the proxy, but we have a much more intelligent implementation now that will find the optimal thread count much better than the old one did. And we're also using that same thread pool by default on the cache service threads as well. There is one thing that has been removed. Well, a couple of things removed, right? I mentioned replicated cache, optimistic cache. We don't have cache mappings in the default cache config for those. You can always add them. We also don't have a mapping or a definition of an invocation service in the out-of-the-box cache config. You can always add it, but the invocable map features of Coherence don't go through the invocation service. That goes through the caching service. So if you want to execute a task within the cluster associated with a particular cache entry, that feature continues to work through caching services. Invocation services was a mechanism to just send a task to a given cluster member, which, while supported, is not the best way to think of the cluster. It's better to think of the cluster in terms of partitions rather than in terms of members. The other reason that the invocation service was removed is from the default out-of-the-box config is purely a practical reason, which is the invocation service works very differently on Extend clients than it does on TCMP clients. And if we had left in support for the invocation service in the out-of-the-box config, a client that was declared to be an Extend client that then tried to access a particular invocation service would silently join the cluster. And while that's okay if you want it, it wasn't something we were comfortable with having happen, by accident. So, we'll leave the definition the invocation service up to those who need it. So there's also a number of sort of random small items in the config space that changed with 12.2.1 that are worth mentioning. One is the coherence jar manifest changes what sort of application it runs when you run java -jar coherence jar. Historically, that started a coherence console that was more or less a debugging tool and not really, well, not exactly meant to be used in production situations. It was more or less a debugger. We've changed the default application when you run -jar to be the default cache server. So java -jar coherence.jar gives you a cache server, and of course a cache server is now a proxy. So this is very meant to be easy out of the box way to start getting your server tier up and running. If you do make use of the console, it's still there. It's still the same class name it's always been. It's just not in the manifest. So that's com tangosolnet cache factory. So you run that class and you'll get the console. Another small change was the default cluster name. I very much recommend that you set your cluster name, certainly for production. If you don't set your cluster name, the default now is the user's name, as in the OS username, '(s) cluster. So for me, I get mfalco's cluster if I don't say anything. Where this is nice is if you have two users on a shared box. So you have some shared dev box for example. Those users can run. They can each run their own cluster, and with the default config, so they can be sharing that cluster port, but they'll get different clusters by default based on their username. And if their local dev box, they have the same username set up on that box, and they start a coherence node there, it would be able to cluster with other coherence instances with that same developer as started. This is obviously not good for production. For production, you want to specify the cluster name yourself. And again, as I mentioned earlier in this slide deck, you want to choose something that is quite unlikely to conflict with other coherence clusters running on your network. Choose a good name. I did mention earlier the default cluster port is 7574. And then the final, well, actually, I think there's one more slide. The final thing on this slide is again small, but as you've noticed, as I've listed system properties throughout this presentation, all the coherent system properties now are just coherence dot something. We've removed the need for the tangasol prefix from system properties. It's still supported. Any coherent system property can start with tangasol, but that's optional, and we retain that support just for existing configurations which make use of it. But all coherent system properties can just start with coherence dot. So the well-known tangasol.coherence.distributed.local storage is now just coherence.distributed.local storage. Okay, and then the final set of miscellaneous features. Multicast is used only for discovery. I mentioned that earlier, but we actually reduced the usage even further. So historically, if you were using multicast-based coherence setup, every cluster member was part of the multicast group. They joined the multicast group as part of joining the cluster. And then we would send some data transmissions over multicast and some over unicast. Well, now all data transmissions go over unicast. And if we're using multicast, it's only for discovery. Because of that, we also want to reduce the amount of processes that are in the multicast group. We want to reduce the multicast load on the network as much as possible. So, for instance, when a node goes to join the cluster, it doesn't have to join the multicast group. It sends discovery messages to the multicast group without having joined it. Those are heard by members of the cluster, and those members reply over unicast, and we finish the discovery process that way. So that limits it. Also, it's not necessary for all members in the cluster to hear a new member trying to discover the cluster. In fact, it's only necessary for one member to hear it, and that would be the senior member. So the senior member joins the multicast group. And for HA purposes, we have the next most senior member, which is on a physically distinct machine, also joins the multicast group. So if the senior member is, for instance, in a GC or temporarily has lost network connectivity, there will be another, and if there is another machine in the cluster, that other machine will be able to respond to the member trying to join to prevent that member from starting their own cluster. So what does this mean? Prior to 12.2.1, every process in the cluster would be part of the multicast group. Starting with 12.2.1, you have at most 2 machines in the multicast group, and Coherence manages it. Your senior dies, and the new senior is on a different machine. That senior will automatically join the multicast group, and will always ensure that as long as there's 2 machines in the cluster, you have 2 machines that are listening on that multicast group. Also related to multicast is which in a multi-home machine, which IP do we use for multicast traffic? Historically, we used the same IP that had been configured for Coherence to use for unicast traffic. The idea was let's keep all of our traffic on the same network so that we could avoid partial failures. Well, now that multicast is intended for discovery only, and that discovery can also apply to non-cluster members, i.e. extend clients, we now let multicast traffic use the IP that's been configured in the OS routing table. So whatever the OS says, routing table says for multicast traffic is where it will go by default. You can still override it, and actually the override element has existed in Coherence for forever. The multicast listener interface element, if you want to specify that it should go on a particular network rather than the default one in your OS routing table. But if you don't say anything, it's going to listen on whatever your OS routing table has been left as the route for multicast. There's also a new kind of global override for all the address selection. This is the unicast listener discovery addresses XML element. It defaults to the wildcard address, which means that any place we are able to utilize all IPs on the box, we will. So this applies to things like WKA Discovery will be listening on all IPs. The Proxy listens on all IPs. If you use Federation, it listens on all IPs by default. And if you wanted to lock things down to just a particular subnet, rather than going through and configuring each one of these things individually, you can set this one element, the unicast listener discovery address, and setting it to a particular subnet in the same CIDR sitter format that we've supported for many releases. You can set it to a particular subnet, and that will constrain all of these various networking features to just that subnet. So for instance, if you set it to 192.168.0.0/16, it means that we're going to find a local IP within that 192.168 subnet, and we'll bind only on that IP rather than on the wildcard, rather than on all IPs on the box. Which is, again, if you're looking to lock down your cluster, that makes sense. Out of the box, the cluster is as accessible as possible, or we're working to make it as accessible as possible, right? We want you to be able to have extend clients connect in over multiple NICs on your box unless you've explicitly told us not to. Another related change is the C++ and .NET clients now include a default cache config. They didn't previously. So if you're using the Java default cache config, the default that's included with C++ and .NET is compatible with it. The only real difference is that because we don't support C++ and .NET cluster members, the coherence.client system property is implied. It can only have one value of remote, so they will always try to connect in through a proxy. And you can use system properties of coherence.address and coherence.clusterport to tell them where to look for a cluster member. And again, the coherence.address can be set to a host name such as Mark's cluster, and we can use that DNS lookup. So we have a series of IPs to look for the cluster. And cluster port, it defaults to 7574 and really doesn't need to be changed. And obviously you can continue to provide a custom cache configuration as well. But for getting started out of the box, we now have something shipping with C++ and .NET that's compatible with the Java cache configuration. So that is it for the zero configuration changes in 12.2.1. Hopefully it does prove to be a bit easier, and if not, if that wasn't an issue for you, the ease of configuration, hopefully you'll see some performance advantages from some of the new defaults, such as the TCP message bus and the auto-sized thread pool. These are things that that should help to improve performance as well as usability. Thank you.